Hey trig class, let's look at the notes from section 7.7. This is the graphs of the other four trig functions: tangent, cotangent, cosecant, and secant. All right, there's what we're going to start off with, tangent and cotangent, and then we'll look at the forms where we alter those, and then we're going to look at the graphs of secant and cosecant, and then the alterations of those. So starting off with tangent and cotangent. So there are the key points that we're going to look at here, just kind of going around the unit circle. In that first quadrant of the unit circle, as we're rotating, there's an angle of 0 degrees. Tangent is 0 at 0 degrees. At pi over 6, tangent is square root of 3 over 3. At pi over 4, tangent was 1. And at pi over 3, tangent is the square root of 3. But at pi over 2, tangent is undefined because, remember, tangent is sine divided by cosine, and the cosine of pi over 2 is 0. So we would be dividing by 0. So there's going to be vertical asymptotes on the tangent function at the odd multiples of pi over 2. So 1 pi over 2, in this case negative 1 pi over 2, 3 pi over 2, 5 pi over 2, and this thing just gets closer and closer to that vertical asymptote, but it obviously never touches it. So it's going to go off like that as we make our way around. Okay, remember, tangent on the unit circle is the slopes of the lines, and as we approach pi over 2, we end up with a vertical line segment, and that's why we go off to infinity like this. All right, so there are those vertical asymptotes that again are at the odd multiples of pi over 2. And the other key thing that I want you to see here is at pi over 4, negative pi over 4, right? And then every pi over 2 units after that, like add pi over 4 plus pi over 2, you'll get 3 pi over 4. You'll get another place where you either get a 1 or a negative 1. Right? So they're always going to be separated by pi over 2 units or 90 degrees that we get back to either a 1 or a negative 1. So there's the big important properties of the tangent function. So all the real numbers have an output except for those odd multiples of pi over 2 like we mentioned. The range consists of all real numbers, meaning in between each of these asymptotes, we go down to negative infinity, we go up to positive infinity in between each one, and each one is separated by pi units. So negative pi over 2 to 0 is pi over 2 units, 0 to pi over 2 is another pi over 2 units. So adding those together, we get a total of pi, and that means that the period of the tangent function, and also going to be the cotangent function, is going to be pi. All right, notice these x-intercepts. The x-intercepts are multiples of pi. That is where sine is equal to 0. So the numerator, again, tangent is sine divided by cosine. So the numerator is equal to 0 at the x-intercepts. The denominator is equal to 0 at those vertical asymptotes. And those are those odd multiples of pi over 2. All right, if you do your tangent function on your calculator, I'm going to do y equals tangent x. All right, do make sure you are in radian mode for this. So y equals tangent x, and then I'm going to do zoom trig, so number 7. And again, zoom trig does from negative pi over 2 to positive pi over 2, and the tick marks are every pi over 2 units. So that's pi over 2, pi, 3 pi over 2, 2 pi. What it does not show are the vertical asymptotes. So there's a vertical asymptote at pi over 2, there's a vertical asymptote negative pi over 2, 3 pi over 2, but that's where this thing is going off to either infinity or as you approach it from the other side, negative infinity. All right, cotangent, same thing except for it falls left to right rather than rises left to right like this in between each pair of asymptotes. So you'll see in between each pair we're falling left to right. All right, and since cotangent is the reciprocal of tangent, everywhere tangent had a 0, right, hit the x-axis, so negative 2 pi, negative pi, 0 pi. Cotangent is now going to have an asymptote there. So there's the negative 2 pi, negative pi, 0 pi. So those are now vertical asymptotes for the cotangent function. Right, so in between 0 and pi, again, that's pi units apart. Right, in between those two, you can see that we fall left to right. We hit 1 and negative 1 at the pi's over 4s, you know, like we saw before. It's just the pattern's reversed. So instead of, you know, the negative pi over 2, or sorry, negative pi over 4 being negative 1, now it's 3 pi over 4 is negative 1. So it's the same, it's basically the same pattern. It's just instead of it rising like this, like we saw for the tangent function, it's falling, from that negative pi, falling to infinity, and then coming from positive infinity and falling again. So it's got some crossover properties, the locations of the ones and the negative ones, but they're being connected in a different pattern than they were in the tangent function. All right, so the big thing is that it's falling left to right, whereas tangent was rising left to right and between each asymptote. All right, Desmos, if you ever use Desmos, it can handle the name cotangent, but if you look in the catalog down here, the second option of the 0 key, it shows you everything that's available. And if you go to, this is now in alpha mode, if you go to C's, where cotangent would be, you can see there's not a cotangent. So there's the CLs, there's the COS's, there is no COT, there is no cotangent function. So the only way I can get the graph of cotangent is to do 1 over the tangent function. So I'm going to do 1 divided by tangent x, and there's the cotangent function. So now it's going to have that property very similar to what we saw before with tangent, but again, falling left to right. It's going off to infinity, it's going off to negative infinity. It's just going off to infinity as we move left between the asymptotes, and going off to positive infinity, or negative infinity as we move right between the asymptotes, positive infinity as we move left. All right, let's look at how we can graph the tangent function if it's been altered. So we've got something that's been altered here. So I'm going to insert something. I'm going to show you the procedure very similar to like I did the sine and cosine alterations in the previous video, how I do those with the tangent function. So the big thing is those vertical asymptotes. So they take place, there's the y-axis, they take place at negative pi over 2 and positive pi over 2. All right. The origin is a point on the graph of the tangent function, and as we move left and right at negative pi over 4 and at positive pi over 4, we hit those ones. Negative 1 down here and positive 1 right here. So just like we had those 5 key points on sine and cosine, that's exactly what we have here. We have 1, 2, 3, the x-intercept, the negative 1, the positive 1, and then we have those vertical asymptotes. Those are our 5 key points. So when I think of them, I think of 1 as the left vertical asymptote, 2 as the left the negative 1, 3 as the origin, 4 as the positive 1, and the 5th as the other vertical asymptote. So again, when I have a function like this, 3 halves tangent x plus half, the things that I'm going to do is determine where are my vertical asymptotes going to go, and then where is that line that cuts through the origin? Where is this point right here going to go? All right, because it's right there on the midline on the thing that cuts this thing into two. Again, they're symmetric, but they're symmetric through the origin. So tangent's an odd function. So where is that 0, 0 point going to go? Those are the questions I'm asking. So the way I determine where is the left vertical asymptote, all right, it's normally x equals negative pi over 2. So the way I alter it is I take whatever is inside the tangent function, and the only thing inside here is x, and I set that equal to the left vertical asymptote. So it's still negative pi over 2. Okay, so if that's said, and we'll see this in a coming section, if that said like x minus pi over 4 or something, then I would set this, x minus pi over 4 is equal to pi over 2. Whatever happens to be on the inside of the tangent function is what I set equal to that left and right vertical asymptote. All right, and likewise, the right one, the positive pi over 2. So again, it's just x on the inside there. So the right vertical asymptote, I'm going to put r, VA, is x equals pi over 2. So the vertical asymptotes have not changed from where they would be on the standard tangent graph. So there's negative pi over 2, there's positive pi over 2. All right, so there's 2 of our 5 points. We've already got our vertical asymptotes taken care of. So we know what we know where everything's going to take place. Now halfway between those, which was 0, there's 0 that's halfway between the two, we hit the midline, okay? So again, that midline is typically, on the tangent function, the midline is typically the origin, 0, 0, between these two. Again, this is what I'm graphing right here. It's just these two and the stuff between them. So the midline is typically at 0, 0. Well, now because of this vertical shift, that midline gets shifted up. So I'm going to draw a little dashed line here. All right, that's the line y equals a half, and that's where that point's going to go. So that's the point 0, 1/2. All right, now what happened beyond that? Well, we went from the midline, we went to the right pi over 4 and up to, again, 1, whatever this number is, okay? But when it shifted like this, think of it as like halfway between the midline intercept 0, in this case, and the right vertical asymptote pi over 2, halfway between that would be pi over 4. Again, we're not altering anything left or right now, because it's just tangent x. Right, and then this would be negative pi over 4. All right, now from that midline intercept at 0, we go to the right pi over 4, and then we went up by 1 before, but now we're going to go up by 3/2 or 1.5. So we're going to add 3/2 to the output that it currently is, which is a half. So adding 3/2 to a half is 4/2 or 2. So that point is going to be at pi over 4, 2. All right, and then likewise, when I go to the left, I go to the left pi over 4 units. And then again, typically I go down 1 unit, but I'm going down 3/2. So I would go down 3/2 from 1/2. So again, 1/2 minus positive 1/2 minus 3/2 is negative 2/2 or negative 1. At this lower number, I'm going to erase the negative pi over 4. This lower number, I will hit negative 1. So this would be negative pi over 4, negative 1. All right, so in between the vertical asymptotes, we go towards the vertical asymptotes, but we never touch them, okay? So we fall to the left towards that negative pi over 4, negative 1, and then we just keep falling towards that vertical asymptote, but never touch it. We rise from 0 towards that point pi over 4, 2, and we keep rising forever as we make our way towards pi over 2, but we never cross that vertical asymptote. So it's going to look something like that. Again, I always graph it to verify. So I'm going to do y equals, clear that out. This is 3/2 times the tangent of x. I'm going to close the parentheses and then add a half. All right, and then I'm going to hit window. Remember, I always change my window. My left side is negative pi over 2. So remember, this is minus, so you want the one underneath the 3. Negative pi over 2. All right, my max is positive pi over 2. All right, I'm going to make my scale pi over 4, just so there'll be some tick marks there where I can see where the negative 1 and the 2 are taking place. All right, then my y max and min are going between negative 4 and 4. I'm going to make that go a little bit higher just so we can see that asymptote behavior, and I'll make it move up in 2s. All right, now let me graph that. All right, so there's that tangent behavior, that tangent look. I can press trace, and now I can plug some points in here, some key points. If I plug in negative pi over 4, I should get negative 1. If I plug in positive pi over 4, get positive 2. All right, and it's just a way to check. All right, if I plug in 0, I should get 1/2. All right, so these are just different ways that we can check our work and make sure that how we're plotting it is correct. All right, so they're doing it with one pair of asymptotes. And then after you get that first pair, you just add pi to all of these points because the period is pi, and you get a repeat, like a copy of everything. So we're adding pi to the left vertical asymptote. Adding pi gets me positive pi over 2. Adding pi over 2 to this one gets me 3 pi over 2. Right? Adding pi to 0 gets me pi. Adding pi to pi over 4 gets me 5 pi over 4. So you can see this is just a carbon copy of what was in between these two asymptotes, between these two, and we could keep that going forever. Just if you want to go to one point to the next, you just add pi, and you can keep on making more and more and more copies of these. Right, the same thing would happen for cotangent. The only thing that's different is cotangent, the left vertical asymptote is at the y-axis. That is a vertical asymptote along with y-axis. the right vertical asymptote is at pi. Technically, the y-axis is the line x equals 0. Right in between those two, at pi over 2, is where the cotangent touches the x-axis. At pi over 4, it's up at positive 1. At 3 pi over 4, make that up here, 3 pi over 4, it's down at negative 1. And it does something similar to tangent, just falls instead of rises. So it looks like that. So once again, what are the things that we need to be able to graph cotangent? We need the left vertical asymptote, the right vertical asymptote, the midline intercept in the middle, and then those values that correspond to the ones. Okay, so these values that correspond to positive 1 and negative 1, they're going to be positive 3 and negative 3 here. Again, because of the shift. Right? And because of the 2, we are going to get some new asymptotes here. Okay, so let me show you the procedure to do that. All right, we start off with setting what's inside the parentheses, inside the cotangent function, equal to the left vertical asymptote that's unaltered. So for cotangent, the left vertical asymptote is 0. So we set 2x equal to 0, divide by 2, we get x equals 0. So the left vertical asymptote is still 0. All right, but the right vertical asymptote is typically pi. If I divide both sides by 2 this time, I get x equals pi over 2. So my two vertical asymptotes, the left one is 0, the right one is pi over 2. All right, so there's again the y-axis, that's x equals 0, pi over 2. I'm going to just dash it over here. There's x equals pi over 2. All right, halfway between those, between 0 and pi over 2 would be pi over 4. That's where we're going to cross the midline. And because we're not adding anything here, we're not adding anything to the 3 cotangent 2x, the midline is still going to be the x-axis. So that is the midline, just like it was for the unaltered cotangent. So that's going to be a point on our graph, pi over 4 and 0. All right, and then we move to the left, halfway between 0 and pi over 4 would be pi over 8. And then halfway between pi over 4 and pi over 2, if you average those, you'll get 3 pi over 8. All right, but you can also do this as 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. You can do it that way. That's kind of how your book would talk about those. You know, find the period is pi over 2, divide that by 4, that's pi over 8, and then just add pi over 8 over and over again. That's your book's technique. I like to do it by halving. So left to right is pi over 2, halfway between would be pi over 4, and then halfway between 0 and pi over 4, the left end and in the middle is pi over 8. Halfway between the middle and the right end, 3 pi over 8. But whatever way works best for you, that's the way you want to do it. All right, and then finally, because this is a 3, the point at pi over 8 is going to be up here at positive 3. So that's pi over 8, 3. And again, I'll need to erase this to have some room. At 3 pi over 8, this is going to be down here at negative 3. Right, and it's going to fall left to right this time, so it's going to fall like that in between the asymptotes. Okay, so there's one period. Again, the period this time is pi over 2. That's our full period. So this time, if we want to get another height that has, input that has a height of 3, we would add pi over 2 to pi over 8. All right, so that would be from here to here. We're adding pi over 2, and so that would be 5 pi over 8. And that would also have a height of 3. So that would be the coordinate of that point. And then we would do it again. You know, we would cross, instead of crossing at pi over 4, we add pi over 2, we'd have 3 pi over 4, and so on and so on. We could keep that process going and get as many of these points and many plots of this little cotangent curve in between as many vertical asymptotes as we want, just by adding pi over 2 to what we have here as many times as we want to do. All right, there's a couple periods of it. Let's graph it again because it's cotangent. There isn't a function on the keypad, so we're gonna have to divide 3. That's the number in front of cotangent. We're going to divide that by the tangent. So 3 divided by tangent 2x. Close that off. All right, if you're not comfortable with just putting a tangent down there, you can say 3 divided by all of this and put a parentheses around all this just to be safe. You don't need it in this case, but if you're unsure when you need parentheses, when you don't, put the parentheses around the entire denominator. What do you want to be in the denominator? Just to be on the safe side. All right, now I'm going to do my window just to kind of make it match what I have here, my original drawing. My left edge is 0. All right, my full period is pi over 2. All right, I'm going to make each little tick mark pi over 8. That was the period divided by 4. All right, and then min and max, I'm just leave it at -6 and 6. So there we cross, and there we start that behavior down towards infinity. Yeah, let me make this go between like negative and 10 just to see that the asymptote behavior a little better. So you can see we're falling to the left forever. All right, trace, just plug in some points. So I can do secant pi over 8 just to show you that we are getting 3 there. All right, and then at 3 pi over 8, 3 secant caret pi divided by 8, I'm getting the -3. So you can just verify that that is what one period of this cotangent function would look like. All right, we're going to turn now to cosecant and secant. So when you graph cosecant and secant, you're actually going to use the sine and or the cosine, depending on which one you're graphing, to be the foundation for your graph. So there's a sine curve. So I want you to understand that the only thing that is the secant here are the blue U shapes, N shapes, whatever you want to call it. These, they kind of look like parabolas, but they're not quite because they do go off to infinity. But what I've got in yellow there, that is the secant function. The stuff in black is the sine, or sorry, that's the cosecant function. The stuff in black is the sine function. So it's actually not really a part of your graph. It probably should be dashed, would have been a better idea here, just to show that it's not actually there, just like the asymptotes are not actually there. But we use it as the foundation. Okay, and the way that we use it, the big thing that we do here is the zeros of your sine function. So anywhere the sine function crosses the x-axis becomes, because cosecant is the reciprocal of sine, those zeros become vertical asymptotes for the cosecant function. And the peaks and the valleys of the sine function, the ones and the negative ones, become the bottoms of these parabola-like shapes that live between each of the asymptotes. So the one for the sine function is also one for the cosecant, but it goes up away from the sine curve, and the negative one, the cosecant function, goes down away from the sine curve towards the asymptotes. Okay, so if you were to graph cosecant again on the TI, and it does not have, there is no cosecant button, but what we can do is I'm going to do y equals 1 divided by the sine function. All right, and just to get back in the regular window that we have, like we have here, I'm going to do zoom 7 for trig, so you can see those shapes. The sine curve's not there. All right, I can add the sine curve to there, and that's going to touch all those peaks and valleys from the cosecant curve. Right, but we use it as a guideline. We don't actually need it. And ultimately, in our final version of the cosecant graph, the sine curve's not going to be there. Okay, but we do plot the sine curve when we make the cosecant curve. In particular, like what I've been plotting on all these examples I've been showing you, is one period of the curve. So the period for cosecant is going to be the same as the period for sine. It's from 0 to 2 pi. So this is what I typically draw for the sine curve. So this part right here is what I'm going to draw for one period of the cosecant function. All right, they're just showing you how we get it to plot on the TI calculators, that 1 over sine. All right, now we're going to do some alterations of the sine curve, which will lead us to alterations of cosecant. So once again, the big things that we're going to do is shift the sine curve first. So for the sine curve, those quarter period points that we plot were the initial point, 2 pi units away was the full period. Halfway between there, we're back on the midline, and then a quarter of the period, pi over 2 and 3 pi over 2, we were at the max and the min, the 1 and the -1. Okay, so for cosecant, that's going to be an asymptote. That's going to be an asymptote. All right, and then these are going to be the U shapes going away from the sine curve. Okay, so that's the way that we're going to do this. It's going to be the same thing as before. We're looking for those 5 key points and where they go for the sine curve. And then we switch to the fact that this isn't sine, this is cosecant. So I start off with, what would the graph of y equals 2, instead of cosecant, I switch to sine. What would the graph of 2 sine x minus 1 look like? So if we recall, the -1, that is going to be our new midline. That's a vertical shift. So that's y equals -1. That's going to be where we're rising and falling from. Okay, because this is just x, there is no shift left or right. There's no squeezing in. The period's going to be 2 pi. So we're going to start at 0, -1. We're going to get back to that midline 2 pi units away, because that's our period. Again, it's just x, so the period's 2 pi. And then halfway between there at pi, we're going to be back on the midline. All right, and then halfway there and halfway there at pi over 2 and 3 pi over 2, we're going to get to those high points and low points. Again, it's positive 2 sign, so we're going to rise initially, and then at this 0, we're going to fall. So at pi over 2, what are we doing? We are adding 2 to this -1. So adding 2 to -1 would get us up to +1. So let's say that that's +1. I'm going to erase that pi over 2 just so I can put a dot there. So that's pi over 2, 1. Right, at pi, we're touching the midline, which is at -1. And at 3 pi over 2, we're subtracting 2 from the midline. So -1 minus 2 more will be at -3. So that point will be 3 pi over 2 minus 3. All right, so there is the sine curve. Anytime we intersect the midline, we're getting a vertical asymptote. So there's a vertical asymptote there, there's a vertical asymptote at pi, vertical asymptote at 2 pi. We're going off of the peak towards the vertical asymptotes. We're going off of that valley towards the vertical asymptotes downward. All right, so again, you can dash this so you don't have to erase it at the end. I'm going to just erase it, draw it back in dashed. But technically, that's not there, so I'm dashing it. It's just like a guide, and there are those key points. Okay, let's graph it real quick, and then we'll graph the 2 sine x minus 1 with it so you can see how that plays that important role. All right, let's look at, first of all, how to graph 2 cosecant x minus 1. So the way we do that is just do the number in front. Cosecant is 1 over the sine, so I'm going to do 2 divided by the sine. All right, whatever is inside the cosecant, we would put that in this parentheses. But since it's just x, we just close that off, and then it's -1. All right, and now I'm going to write the exact same thing, but without the division in there. So this is 2 times the sine of x minus 1. Now, one thing that you can do is you can move your cursor back. There it is on the equals. If I go back again, notice it's on the thing that's in front of y2, this little slash. I can hit enter. There's a bold line. I can hit enter again. There's like a shade above, shade below. But then this last one is dashed, like dotted. There it is. Sorry, dotted. So you have to hit it a couple more times. There's dotted. Again, you don't have to do that, but that's just to show you that it's not really there. So then if I graph it, there's the cosecant, and here is that sine function, okay, that we can see is in there. Let me actually do my window like I've been doing. 0 to 2 pi is 1 period. All right, and then I'm going down all the way to -3. I'm going up all the way to +1. I'll graph it. So there's that sine function. Oh yeah, I need cosecant, so I need to make the window much higher than a peak in the valley. So let's do -10 to 10 again, just to have the ability to see those asymptotes on the cosecant. All right, so there's the left one, there's the right one. So when you've got a full period in there, you're going to see the you're just going to see one that goes up to positive infinity and one that goes down to negative infinity. And depending on the signs, that's all you'll see for one period of cosecant and secant.